Today, we will continue the discussion about length filter, and in particular, we will talk about the basis filter. Last week, we talked about the state in our length following task. The state is essentially the D and the phi. And last week, we also talked about how to vote from each detected segment. Okay, so you guys must be familiar with this measurement model, or in our code we call it measurement likelihood. Today we will keep going. We will try to estimate the belief of of the robot. So that means that the measurement could be noisy and the robot think where it is, and it is not the exact location. It is a probabilistic distribution. Before we do that, maybe we can have a very quick refreshment for your probability. So I think everyone took this class sometime maybe 2 years ago, or maybe not a long time ago, right? So I want to make sure that everyone understand what's a random variable. 例如有没有什么例子好了？有没有？掷骰子，好棒，对。那 OK。掷骰子那是discrete random variable, right? Okay, great. How about the mean and variance? 还是说要什么平均数啊、标准差？这样可能大家就比较知道哈。Probability density function. Okay, normal distribution 常态分布，对啊。其实好像讲中文大家都知道了哦，然后写成英文好像大家不太记得这样。Okay, 那how about like Gaussian distribution? Yeah, very similar to this one, right? Let's just do a very quick review of those terms. Let's donate x as a random variable, and it could be discrete or it could be continuous. 那掷骰子是一个非常好的例子。The outcome could be 1 to 6, right? And we assume that this is a fair dice, and each outcome should be like 1 divided by 6. Okay, so discrete random variable. And we also have a continuous random variable. Okay, and this is a function called probability density function, and we will call it just a PDF. Okay, and you can see maybe this one is like a normal distribution. And probability from A to B is more like the integral from the point A to point B, probably more like the area under the curve. Okay, so this is just one-dimensional. So you may see this a little bit familiar because we will look at this example later. In this code, we have the mean vector, and that the two-dimensional, one dimension is E, the other one is phi. Okay, just like what we had last week. And you can see the code here, and we also have a covariance. It's a 2 by 2 matrix. RV is a random variable here, and we just assign a normal distribution to it by the mean and the covariance. Okay. And this is the PDF. Okay, that's the probability density function. And the belief, RV. So belief is actually what we want to know in the whole process. Okay, and over here, we want to know what's the lateral distance D and the phi. So that's our state, right? Okay, so when we draw it, it will look something like this. So does that make sense? Okay, and also something about the joint and conditional probability. So maybe we talk about the dice, and we should also talk about the poker, right? 因为赌性坚強嘛，對不對？哈。Okay, suppose we have the joint probability P xy, and this is an abbreviation from P x equal to lowercase x and y equal to lowercase y. Can anyone tell me what's this? If you are playing a poker, then what's the probability you can get diamond 4? 52分之一，对不对？不算鬼牌哦，不算鬼牌。好 ，How about this? 一样。Okay, because we want to figure out the points is 4 and the color and the shape is diamond. Okay. So that's the joint probability, very straightforward, easy to understand. How about the conditional probability? So P x given y. Okay, so we have an equation here, but maybe we can just look at an example. That could be easier, right? How about this? Can anyone tell me what's P of 4 given diamond? 13分之一. Great. Okay, so as you can see, this is just like what you guys predicted and also the same. And we can actually verify it. How do we know, like for example, this one, this is actually P of xy divided by Py, right? And over here, y is the diamond. So what's the probability for P of diamond? Y equal to diamond. 4分之一, right? So you can do the math, you can do the calculation there to verify. All right, so we are done with the review of probability. So as long as you know all those, then it should be good enough. Okay, so again, the belief of a robot, and this you will see this quite a lot in many different robotic applications. Okay, so in our case, land following, we just need to know the d and phi, right? But maybe in some other case, you want to know the robot pulse, for example, in 3-dimensional, then that could be x, y, z, and the rotation. The definition is here, the posterior distribution over the state of the environment given all past sensor measurements and all past controls. Okay, and the basis filter here is the most general algorithm for calculating beliefs. This algorithm is fairly short, probably you can say simple. Essentially, we will look into the line 3, and in the textbook, we call it control update, and sometimes it also called prediction. And the line 4 is the measurement update. Sometimes we also call correction. Okay, so when you see prediction or propagate or control update, that means this one, this function. Okay, and for the measurement update or correction, that means this. We will see something very similar in the landfilter.pdf. The equation 2 in the document, you can see this step and this step. Okay, so essentially in the document call it predict update cycle. A PDF of this part, essentially this part, is the process model. Okay. And this part, PZT given XT, is the measurement model. And this is exactly what you guys have already done last week. That's the measurement likelihood. Again, so let's take a close look into the first PDF. We also call it state transition probability. So that means if you have the state and the other state. So over here, that's the state t-1 to state of t. And the probability here is called, we call it the state transition probability. And you can also see another variable here, ut. And u is called the robot controls. Suppose you have a robot maybe over here. So the robot control could be that the robot push the door and state of the door changed. Okay, or it could be a mobile robot with the wheels. So you ask the robot to move their wheels for maybe some gain or omega for a certain time. Okay, and the UT will change the state from t minus 1 to t. Okay, so we call this a state transition probability. Okay, so in this step, is there anything about the measurement? Actually, no. Okay, we don't, in this step, the transition is only changed by the control variable. In our example, the control variable in our case is the velocity and the angular velocity. Okay, we will also mention this just a little bit. Okay, and for the second part, you guys already calculate the measurement likelihood. You remember that, right? So you guys vote to the measurement likelihood, and one of the point become red, and the others are blues, right? Okay, and you can see that over here, actually, the measurement probability here is not depend on time too much. So sometimes we also write it as P of Z given X. Well, it would be easier if we look at a real example. There is a robot here. In this example, we want to estimate the state xt, and the x is the state of the door. Okay, and the door could be either open or closed. And at time is 0, and we call it a prior probability. The door could be open, the probability is 0.5, and the door could be closed, 0.5. The state here, the random variable is a discrete random variable, right? And the value could be just open or closed. So when you see this robot remind you for anything, this is a famous robot. And this is a famous example. So I'm very happy that we can work on this example together. Because when you say, oh, I'm doing something about robotics, you should know this robot and you should know this example. Okay, so does this ring any bell for you, this robot? 有没有人看过《星际大战》的？宅男没有看过《星际大战》，你还叫宅男吗？对不对？还是要美国宅男才那个？我跟你讲，美国宅男看到《星际大战》，他们全部疯狂你要跟美国阿仔做朋友，一定要知道《星际大战》。你知道那时候《星际大战》第几集出的时候，就是有那个 BB3 嘛，他们那个就变成有人就扮成莉亚Prince Leia， 就绑2个这样子就来了。然后蛋糕弄成一个那个 BB 什么的，就是有一只 robot 有没有？对啊。这个要看哦，没有看过《星际大战》Star Wars， 然后你说你喜欢 robot， 这谁相信？然后这只有印象了吧？对不对？叫做什么？有没有人知道？这只叫 R2D2 啊，对啊，就是 R2D2 啊。其实那个电影好像很久以前就拍了，对不对？好像是不知道是196集吗？还是197集？那时候很久以前就拍了。然后对这些美国阿仔来说啊，他们的梦想就是做出一只 R2D2， 所以你可以看到右下角有没有？右下角这只 robot， 它其实有点仿照那个 R2D2 的感觉。然后这个是在 MIT 的体育馆里面，然后他们就是放了很多那个跨栏的，然后让 robot 在里面跑来跑去。那这个也大概是90年的吧。那时候 MIT 就做了一只像这样的 robot. This example is extremely important. Yeah, I'm very happy and exciting to walk through this example with you guys. Let me introduce you some of the variables here. So the first one is Z. So Z is the measurements here. And because the robot's sensors are noisy. Noisy means that when the sensor tell the robot the door is open, it may or may not be open. So if you have a perfect sensor, when the robot senses the door is open and the door state is actually open, it's only 0.6. Okay, so it's not very reliable to detect when the door is open or not. And you can see that those two will sum up to 1. So that makes sense. And you can see that the sensor is relatively reliable when the sensor sees the door is closed and given the door state is actually closed, that's 0.8. That's relatively reliable than the open case. Okay, so we will have some of the conditional probability here, and we will also talk about the control here. Okay, and in this case, the robot has a manipulator, and it can push the door open. And if the door is already open, it will remain open. Okay, and if it is closed, the robot has a 0.8 probability that it will open the door. The robot, the manipulator is not very good as well. So when it pushes the door and only 0.8 chance that the robot will open the door. Okay. So not very reliable sensing and not perfect control. Okay, and actually this is the real world. Okay, and the robot can also choose to do nothing. And when robot choose to do nothing, and the state of the door is not going to change. So this is something we know here. So we have the prior, t is 0, and the prior probability for the door 0.5, 0.5. Okay. And now we have the time is equal to t. And in addition to the prior belief of x0, we already know that the control is u1 is do nothing. Okay, and the measurement z stands open as an input. So you can see the equation like this. So this is what we are going to estimate. So through the whole process, we are going to observe what the belief is going to change. Okay, so this step, can anyone tell me which step is this? We have two steps, right, previously. One is called prediction, and the other one is called correction. Or you can say control update and measurement update. Okay, and this one is definitely control update, right? Okay, and you can see that actually this is a discrete case. We can break this down as P of x1 given u1, the control variable, is do nothing. And this is a joint probability. Robot do nothing, and the sensor door is opened. Okay, and times the belief, and this is actually the prior, right? So this part is actually 0.5. We will have to have a summation of the x of at time equal to 0. So we will have this term plus this term. Okay, because at time equal to 0, the x0 could be either is open or is closed. Right? Does that make sense? Over here, we just need to fill in the numbers. Okay, so you can see that this part, the prior, this part is 0.5, no problem. And this part is 0.5. When a robot do nothing, the state, it will remain open, right? So that would be 1. So this term is 1. Okay. And we also need to figure out this term. Well, the xt equal to is open and u1 do nothing. and x0 is closed. That would be 0. Right? So we get 0.5. Likewise, when x1 closed, so here this is open, and this is closed, and we can do the same thing, right? And we also get a probability of 0.5. Okay, so far you see that this doesn't really change anything, right? The prior door is open, is 0.5. This part is 0.5, and if the robot do nothing, it will remain 0.5. Okay, so far so good, but because the measurement, the sensors are noisy, so that means when the sensor see the door is open, there is some chance that it is not. Okay, so let's take a look at the second part of the equation. So that would be the measurement update. Again, we have two possible cases: is open or is closed. Okay, and you can see this. Let's take a look at is open for now, and this part is calculated from previous step, right? 0.5. And how about this? We will have to know what's the probability of Z1 equal to sense open, and the door at t equal to 1 is actually open. And in this case, the probability is in the front of your page 2. Okay, that would be 0.6. Okay, so you got 0.6 times 0.5. We have a parameter here, and we will explain this very shortly. Okay, and again, the state of the door at t equal to 1 is closed. We can look up those probability, and you can get 0.2 and 0.5, right? Okay, and this is called a normalizer, okay? And it is now easy to calculate. So we can 0.3 and 0.1. We just need to sum those to 1. Okay, and therefore we get what we want to estimate at t. The robot believe that door is open 0.75 and is closed 0.25. Okay, and you can see that because the sensor is noisy, so you actually get a different result than its real, like 0.5, 0.5. So now we have t equal to 2, and our U2 is to push. So at t1, the robot actually do nothing, right? And at t equal to 2, the robot push the door. And the sensor, again, tell the robot that the door is open.
第一条 belief bar x2 等于 open， 然后先照公式嘛，就是这样子，就是当 x1 等于 open 的时候，然后你的 control 是 push， 然后 x2 是 open 乘上在 x1 等于 open 的时候的 belief， 然后加上下面这一行，变成 x1 是 close 的时候这个。那根据原来的式子，原本如果是 open 的话，那你去 push 它还是 open 的几率就会是1。那 x1 等于 open 的几率在刚算出来是 0.75， 然后如果原本是 close， 你去 push 的话，它变 open 的几率是 0.8。这边的话，式子都是在第3面的 PPT 那边，所以你把这式子乘出来就得到 0.95。然后再来是你要求 x2 是 close 的时候的 belief bar， 那一样把式子写出来，原本 x1 是 open， 然后 u2 push x2 close， 然后 x1 open 的 belief， 然后加上 x1 open u2 push x2 close 乘上 belief x1 等于 open 的几率。那因为你原本是 open 的话，你去 push 不可能变 close， 所以它几率是0，然后乘上后面 x1 等于 open 的 belief 是 0.75， 然后如果你原本 open， 然后 push， 然后会变成 close 的话，它的几率是 0.2， 乘上 0.25 会等于 0.05。然后验证的话，因为它们两个几率加起来一定要是1，所以 0.95 加 0.05 是1，所以这个值是正确的。
用前面算出来它的预测就是 0.95， 然后再乘上它实际上就是翻到最前面那一页，第2页有讲说门是 open， 然后 sensor 预测也是 open 的几率是 0.6， 然后再乘以一个就是修正项 eta， 然后会得到就是 0.57， 然后这个是刚刚的 0.05， 然后乘以它sensor 原本是 close， 然后 sensor 预测是 open， 一样乘一个 eta 会得到这个 0.01 eta， 然后因为他们两项加起来答案要会是1，所以就可以算出 eta 等于1分之 0.58， 然后把它乘上去就是答案了。
We just have the answer here, and and this is a more like detail, like which one you need to pick. Let me just quickly explain. I add something to the length filter that IPyNB last time. So if you do git pull, and then you will see another file called lengthfilter2.ipynb. And let me just explain this, some theoretical background, just a little bit. So last time we just assumed some coordinates, right? P1 and P2, right? So last time just put some values in there, but we don't really know that what those values should locate in your image. So today we add something from the ground projection. Because this part in the repo, it is written by C++. But don't worry, we already have some re-implementation in Python and in the lengthfilter2.ipynb. Essentially, as long as you finish the step D, the calibration, you will get a homography. That's a 3x3 matrix. And it's easy that if you have a point on your image, something like this, and you have your homography here, and you can get your 3D point on the ground. Okay, so assume that you already get a very good extrinsic calibration. And you can see that some calculation over here so that you will get X, Y, and Z. So this is the second exercise we are going to do in a moment. And different from last time, we have a ground projection cell. So if you have your laptop ready, please just do git pull and go to the tutorial Python folder and just do Jupyter Notebook lengthfilter2.ipynb. Okay, and you will see this part, the ground projection, and the generate vote and measurement likelihood. This is what we did last time. Okay, and today we will try to integrate the measurement likelihood into the belief we actually want to calculate in this step. Okay, and you will see a cell called Initialize Belief, and we actually have seen it when we introduce a probability density function. Okay, and we skip this part for today, but actually you can see the code. In the code, it is called propagate update, and this part is actually something like this part. This part is about the control. And in the control update, in the code, you can assume a given velocity and the angular velocity. For our Duckiebot, if you don't have other sensors, so we can skip this part for now. And the next step will be the measurement update. So this will be something like this part. And the measurement is from your camera, and then line segments, and then D and phi. So that's the measurement. Okay? And finally, we want to calculate the belief of the state X at time equal to T. Okay? And then finally, we want to generate the length pulse from the belief. We have seen this already. So as long as we can have the mean and covariance, and we can have like a normal distribution, and it will look something like this. Okay, so when we set a mean vector 0, 0, so what's the assumption here? So this is actually the more like the prior probability, just like what we had. That's another example. Okay, so what does that mean? The prior we give it 0, 0， 角度没有错，就是位置跟角度。好，其实我们把它设成0， 0，就是把 d 跟 phi 的 prior 都设成0了。那设成0代表什么？假装这是 Duckietown 好了。那你其实你要放在，就是 d 大概要放在0的位置。好，然后你的角度那个 phi 也要大概放在0的位置。好，那它就这样就会符合你这样一开始的prior probability 这个设定。You can see the covariance here. We have 0.1 and 0.01. So this part is actually for the D, and this part is for the phi. It's more like you aim at some variance of this random variable. Okay, so you can see this in this direction, right? So this is about the covariance equal to, in this direction, 0.1, and the other direction, 0.01. Okay, and sooner you can actually play with those numbers. And you will see this more like a normal distribution to generate somewhere else in this figure.